Since the lab failed on Thursday, we're going to go ahead and have two sessions today. So right now, the 12 o'clock session, and then tonight, the 8 o'clock session. And again, no pressure if you can't join. It's perfectly fine. It's just I want to get this out for y'all and make sure it makes sense because this is an important chapter, right? To get on my soapbox a little bit. Everything that you're learning in layer 2 will prep you for everything that you will learn for layer 3, right? To speak in detail, learning about the spanning tree, learning about timers, learning about how the theory actually operates behind the scenes, right? Using Wireshark to actually see what the communication looks like between, you know, looks like between switches and what have you, what those BPDUs look like. You guys are going to have to understand what that means, right? What it looks like, so that whenever you're taking the exam, you have nobody to consult except for yourself. Okay. And you can consult yourself better with practice, reading theory, and of course, understanding the who, where, what, why, and how. Okay. All right. So let's jump in, right? So we are on chapter 9, right? And we're talking about spanning tree protocol concepts. Okay. Right. In its simplest form, right? Spanning tree allows, right, local area networks to have redundant links in local area networks while overcoming the known problems that occur when we're adding these extra links, right? What are these known problems that I speak of, right? So without spanning tree, right, and we'll get to talk about theory in a little bit. Without spanning tree, there isn't any mechanisms on redundant links that would stop a Ethernet frame from traversing constantly. Okay, so let's say PC5 is trying to communicate to PC4, right? PC4 is right here, right? Switch 1 gets it, right? And you guys know about the three major functions of the switch, right? The switch is going to learn MAC addresses, is going to forward frames, right? Based on destination MAC addresses, right? Let's leave out that third, right? A main function of a switch, which is loop prevention, right? That's where spanning tree comes in. What switch 1 is going to do is going to do its two first major functions. It's going to forward that frame, right? And switch 1 is going to get it. And let's say switch 1 doesn't know about the MAC address, right? Because we're at layer 2 right now, the MAC address of PC4, right? Switch 1 is then going to perform, right? It's going to be in a condition to where you guys learned about, which is unknown unicast broadcast, right? And what that is doing, it's going to forward, right, this frame, right, that's trying to get to its destination out of all ports. It's going to do a broadcast message, right? And until it gets a response, right, then it's going to go ahead and forward that frame to the proper destination, the proper port, or what have you. But without that, unknown unicast broadcast is going to say, hey, switch 1, we're going to send it out all ports except for the port that I received it on, right? It's going to do that. Switch 3 is going to do the same thing. Hey, I'm going to send it out of all ports I received it on. Okay. Switch 2 is going to do the same thing. Hey, I'm going to send it out on all ports you know, versus the one that I received it on, right? So it's going to send it out. Okay. It's going to send it out. Oh, but we have a host here. It's going to send it out. Hey, it got to the host. Now I'm going to go ahead and reply. Boom. We're going to get here. But now we still have constant broadcast that's happening. We don't have a mechanism that's blocking certain ports that's saying, hey, there's only one flow of traffic. Okay. So now we're just seeing traffic constantly go back and forth, forth and back. It may reach it, right? It may reach PC5, right? But we're still getting it to the point to where the CPUs on these switches are getting overburdened, right? We're performing calculation, we're performing with the control plane, interacting with the data plane and saying, hey, here's where you need to go, right? Because it's getting punted. It's always getting punted up to the control plane, to the CPU. So when it gets punted, it has to re-engage back with the data plane and say, hey, hardware, here's where you need to send it, X, Y, and Z, right? And so when it keeps doing that, it's getting overburdened to the point to where now CPU utilization. Because again, these frames are being sent by the minute, right? So with that, when that happens, we get to a state to where CPU on our switch is at 99% or 90%. Now the switch can't function. So now what we have is this switch is stalled. This switch is stalled. This switch is stalled, right? And we have the condition of a broadcaster. Okay. All right. So with that being said, right, with the mechanism of spanning tree, right, um, being in place for, local area networks that have redundant links. Okay. And what I mean by redundant links, right, just to go ahead and make sure you guys make sense, right? There's two ways from switch two's perspective. There's two ways to get to switch one. I can get to it directly, or I can get to it through another switch. Switch three perspective, I can get to switch one directly or through switch two. Switch one, I can get to switch three directly or through switch two. That's redundant links. Okay. All right. So, right. So, what is spanning tree going to do? Right. Spanning tree, what it's going to do, it's going to go ahead it's going to block certain ports so that there is one flow of traffic. Okay. So spanning tree might say, hey, we're going to go ahead and block this port, right? And I'm going to forward traffic on this port. I'm going to forward traffic on this port, and I'm going to forward traffic on my root port, right? And let's call this the root port as well. Sorry, guys, my writing is terrible, right? And then we're just going to be forwarding, right, on my designated ports, right? So now, if PC4 is sending traffic, right, to PC5, right? Boom. Even by accident, traffic is going to get there and it's going to be dropped, right? Switch 3 is going to say, hey, I'm blocking any traffic that's coming here, right? Except for BPDUs. I'm going to go ahead and send it up here because I only have two ways to get there, right? Boom. One-way flow of traffic. Let's talk about it from switch 3 perspective, right? If I had a host, right? If I had a host sitting right there, I'm going to go ahead and just send it up my root port. I can't send it here because it's blocked. I'm going to send it here and then send it to PC5 or send it to PC4. But there's only one flow of traffic. There isn't multiple flows of traffic. Okay? All right. Let's go ahead and let's move on, right? So we spoke about the need for spanning tree, right? We spoke about some of the basics and what have you, right? And we spoke about a broadcast one, right? I spoke about one class of problems, right? That's caused if we weren't using spanning tree within a redundant local area network. And I said broadcast storms, right? And broadcast storms, of course, the forwarding of a frame repeatedly on the same links, consuming significant parts of the link's capacities, right? That is the actual definition of it that you guys will need to know for the exam, right? A broadcast storm is the forwarding of a frame repeatedly on the same links, okay? Consuming significant parts of the link's capacity. But here's another one, right? Here's another one that we didn't speak about yet, right? Another class of problems that happens if we're not using spanning tree is MAC table instability, okay? The continual updating of a switch's MAC address table with incorrect entries in reaction to looping frames, resulting in frames being sent to the wrong locations, okay? Right? So if this MAC address reads PC's 5 MAC address here, right? We're not using spanning tree, right? Just like we talked about. There's broadcast storms all over the place, right? And again, we talked about the three major functions of a switch. Those first two functions, it's doing its job. It's forwarding frames, right? So switch 3 is sending that frame that it received regarding PC5 from its switch, right? Switch 1 gets in and said, oh, Switch 5 lives over there. Now I'm confused, right? So now what are we going to have, right? We have a source, we have a MAC address table entry for PC5's MAC address on gigabit 0/1. We also have a MAC address entry for PC5 on gigabit 0/2. MAC table instability, okay? This is what not using spanning tree does to your environment, okay? All right. And last but not least, we've spoke about it. You guys seen it with broadcast storms, and of course, my explanation. The last class of problems that you'll get with not using, when not using spanning tree and redundant local area networks is multiple frame transmission, right? And again, this is a side effect of looping frames in which multiple copies of one frame are delivered to the intended host, confusing the host. Okay. All right, let me take out my pencil, right? So PC5 trying to communicate with PC4, right? Multiple copies, right? So switch 1 is doing its first 2 jobs, leaving out loop prevention, right? Okay, so this is what's happening, right? So PC4 is getting multiple frames. It's getting a frame that's sourcing from switch 3. It's getting a frame that, of course, is coming from switch 1 via switch 2, right? But it's coming from all over the place. Okay? So these are the 3 classes of problems of not using spanning tree in a redundant local area network. Broadcast, and you need to know this for the exam. This is a key topic, right? Broadcast storms, MAC table instability, and multiple frame transmission. Okay? All right. So again, what does spanning tree actually do, right? Just like I showed you guys earlier, right, from a high level, right? Spanning tree, right? It places each switch port in 1 or 2 states, a forwarding state or a blocking state, right? Interfaces with a forwarding state, they act normal. They forward and receive frames. Interfaces in a blocking state, however, do not process any frames except for messages related to spanning tree, right? That's it, right? So BPDUs or what have you, anything related to spanning tree, nothing else. It does not forward, how do I want to say this? It does not forward user frames, right? So frames coming from users PC or what have you, it does not, right? So again, what is spanning tree doing? It's going to go ahead and say, hey, we're going to go ahead and either block or forward traffic on certain ports, right? We'll use B and F, right? So that's what it's going to do. Okay, right? That's exactly what spanning tree does, right? And make sure there's one flow of traffic. Okay, right? For the exam, you guys will need to understand the concept of convergence, right? The whole term of it is STP convergence, right? And what that refers to, right? That refers to the process by which switches collectively realize that something has changed within the local area network, right? Within that topology, and determine what they will need to change, right? In regards to like ports, right? Either they need to block a port or they need to forward a port. That is what it means whenever you read about convergence or what have you. Okay. So um so what does that mean, right? What does that does, right? So the switch, right, spanning tree protocol, right? It works off of, and this is not in the exam, by the way, right? It works off of an algorithm, right? And that spanning tree algorithm, right? It creates a spanning tree of interfaces that forwards frames. Okay, right? And that tree structure of forwarding frames creates, and you heard me say it before, that tree structure of forwarding frames creates a single path to and from each Ethernet link, right? So I can trace a single path, right? I can trace a single path from one PC to another, just like you can trace the base of a tree to each leaf. Spanning tree. Okay. All right. So hopefully that makes sense, right? If you can trace the base of a tree to each leaf, right? That's exactly what spanning tree is doing with their algorithm. You can trace each port, right, to another port by just one path, not by multiple paths. Okay. All right. So what is the criteria, right? Whenever the switch, right, or the switch that's operating in spanning tree, whenever it's trying to choose whether to put an interface in a forwarding state. Okay. So first things first, right? Spanning tree elects a root switch, right? And we'll talk about root switch elections in a second. Okay. So whenever it collects that root switch, right? The switch is going to say, right, spanning tree for that root switch puts all of its working interfaces on that root switch in a forwarding state. Okay. All right. Next, in each non-root switch, right, it calculates the least cost path between itself and the root switch based on spanning tree interface costs, right? The switch port that begins that least cost path is the root port, okay? And the cost is the switch's root cost, okay? All right, last but not least, right? Each physical links connects to two devices only. With two devices on the link, the switch with the lowest root cost becomes the designated switch. And again, and this is in regards to non-root switches, right? And I'll talk about this in a second. With two switches on a link, the switch with the lowest root cost becomes a designated switch. And its port connected to that link is a designated port on that link. Okay. And we're talking about interfaces within spanning tree that get put into a forwarding state. Let's do some convergence real quick. Okay. So let's get my pencil, right? So, and I won't spoil it just yet. Okay. So first thing a switch is going to do that's operating in spanning tree, right? It's going to elect its root switch. Let's say switch one is the root switch. Okay. That's a terrible king crown, by the way. So it's the root switch, right? Just like I stated, right? The first thing, right? The criteria that Spanning Tree uses, right, to go ahead and put an interface in the forwarding state. If it's a root switch, all working interfaces on a root switch will be placed in a forwarding state. Okay, so we're going to put F right there. It's in a forwarding state. Okay. Each non-root switch calculates the least cost path between itself and the root switch. Okay. Let's say, right, if we're looking at switch two, let's focus on switch two for a second. The path to get to switch one, right, is 4. The path to get to switch one via switch three, we have 4 right here, and we have 4 right here. To get to switch one via switch three is 8. To get to switch one via gigabit 0/0, right? It's 4. It's a path cost of 4, right? So based on the second point that I told you guys as far as placing ports in a forwarding state, right? Each non-root switch is going to say, hey, what is my least cost path to the root? Oh, it's 4 versus 8. Great. I'm going to place this in a forwarding state. Okay. But this forwarding state, let me get my eraser, right? With this, and where's my pencil? There we go. All right. So with this, right, it's going to have a special name for the port, right? It's going to be in a forwarding state, but the name of the port is going to be called a root port. Okay. All right. It's going to be called a root port, right? And it's going to be in a forwarding state. Okay. Same thing with switch three, right? Let's imagine, right? Same cost, right? But again, the non-root switches, they're calculating what's the least path cost to the root. 4 versus 8, 4 is going, the lowest one is going to win always. So this is going to be my root port, okay? And I'm going to be forwarding, okay? All right, all right. Now, there's another thing, right? The last point that I made, right? Between two non-root switches. These are, let me change the color so it can make sense. These are your non-root switches. Switch 2 and switch 3, right? We need to do something about this, okay? We need to go ahead and say, hey, which port on this link is going to be in charge of forwarding, right? Right? So switch 2 and switch 3 are going to send messages, spanning tree messages to each other, and they're going to say, excellent, right? The switch, I apologize, the switch with the lowest root cost, right? You're going to become the designated switch, okay? Right? So switch 2 has a path to the root with a path with a cost of 4. Switch 3 has a root path cost to the root with the cost of 4. Okay. I'm not going to spoil it just yet. We're going to get to that point. Let's say, right? Because once there's a tiebreaker, there's another criteria that's used, but we're not going to get to that just yet, right? So we're going to imagine that switch 2 wins. Switch 2 becomes that designated switch. So it's going to say, hey, excellent. I won. I'm going to become the switch that my port become outside of my root port. This port becomes a forwarding port, right? It becomes a port that has the state is forwarding, but the role is a designated port because I am the designated switch on this link between non-switches, non-root switches. Okay. Okay. So let's talk about some of the reasons, and this is very important to understand for the exam. Let's talk about the reasons for forwarding or blocking, right? In regards to the characterization of a port, right? So we already discussed all of the root switches ports, right? They're going to be forwarding, right? The root switch is always the designated switch on all connected segments, right? So between switch 2 and the switch 1, which is the root, right? From that standpoint, switch 1 is always going to be the designated switch. Between switch 3 and switch 1, it's going to be the designated switch, right? It's going to be forwarding, okay? Right? It's always going to be forwarding. Those states on those interfaces, it's always going to be in a forwarding state, okay? Each non-root switch's root port, okay? It's always going to have a state of forwarding, right? Again, what you guys learned, the port through which the switch has the least cost to reach the root switch, lowest root cost, it's always going to be forwarding. So let's review what we learned. On this link, okay, right? Let's talk about the characterization of a port, right? From the root switch, all of its ports are always going to be in a forwarding state, right? It's always going to be a designated port. The non-root switch, we're talking about switch 2 to switch 1, right? Its calculation to switch 1, right? Gigabit 0/0 to gigabit 0/0 on switch 1, that is the root port. That is always going to be in a forwarding state, okay? So for this link, both sides, right, of these interfaces on each switches are always going to be in a forwarding state. That is its spanning tree state, okay? All right. Same goes for that link between switch 3 and switch 1. Okay. Let's talk about, right, each local area network's designated port. Okay. So for the example that we spoke about between the non-root switches, switch 2 to switch 3, right? Switch 2 won the election. It's a designated switch, right? And it has a forwarding, it has been assigned a forwarding state but the role is called a designated port. Okay, right? And what does that mean, right? This switch forwarding the hello onto the segment, right? And this is the switch with the lowest root cost, right? And it is the designated switch for this segment. This is a segment, okay? Another name for a link, okay? This is that segment right here, okay? So, with that being said, what about all other working ports? Because we converge this port, gigabit 0/0. We converge these ports, right? All other working ports, we converge this port, right? All other working ports are going to be in a blocking state, right? And the port is not used, right? The port is not used for forwarding user frames, nor any frames received on these interfaces are considered for forwarding. Okay? This is our convergence. Okay? All right? Okay. Let's go ahead and what else should we talk about? We got some time left. You know what? That'll be great for later. Okay, so let's stop here, right? We're gonna stop here and we're gonna come back 8 o'clock tonight to go ahead and discuss more about spanning tree, right? We're gonna jump right into talking about, how spanning tree works. We're gonna talk about what a bridge ID is and the hello BPDU. We're gonna speak about, more in depth about convergence, right? So choosing the root port. We're gonna go over it again and again and again, and we'll do a lab, and then we'll talk about some details in regards to actually calculation, right? Because my goal here is right, and this is a little bit of theory for myself. You guys can let the CPU and let the switch calculate, right, spanning tree for you. You become a more distinguished engineer if you can calculate spanning tree on paper for yourself, right? Because again, like I was stating earlier, is that you will be the only person that you are able to consult on the exam. Okay. With that being said, I'll hop off my soapbox and I will talk to you guys at 8 o'clock.
All right,
All
thanks,
right.
Gabe.
All right,
Thanks,
guys.
Gabe.
Bye.
All right.